Okay, this is a two-part lesson on electric potential, which also is called voltage, and capacitors. And all the images that you see in this video are from OpenStax Physics, which is a publication of openstax.org, distributed under the Creative Commons Attribution License, version 4.0. The first part of this two-part lesson deals with the concept of voltage, which is also called electric potential. This slide shows what happens to a positive charge, Q, right here, as it moves through an electric field between two parallel charged plates. In this chapter, we'll learn that a device such as this is referred to as a parallel plate capacitor, and the electric field between the charged plates is more or less uniform, meaning it has the same magnitude everywhere except for at the edges where there's some boundary effects, and the same direction everywhere. It's a uniform electric field. So what happens is this positive charge will go zip across from positive to negative along the electric field lines. It gets pushed in that direction because it experiences an electrostatic force. In last semester, you learned that there's a connection between the work done by certain forces called conservative forces and potential energy. And it turns out that the electrostatic force is a conservative force, just like gravity. So when the electrostatic force does work, there's a change in electric potential energy. And the connection is the work done is equal to the negative change in electric potential energy. So first recall that work is equal to force times displacement times the cosine of the angle between the force vector and the displacement vector. So for the case of the positive charge plus Q, in this picture, the electric force points to the right. It gets pushed in the direction of the field lines, and the displacement is in the same direction. So the angle between those two vectors is 0 degrees. So for the case of this particle, the work done on it by the electric force is simply F sub E times D, the distance traveled. Now, since electric field is the strength of the electric force per unit charge, the electric force is the electric field times the amount of charge. In other words, F sub E, the electric force, or electrostatic force here, equals E times Q. So let's plug that in. So the work done on this positive charge by the electric field is EQD. And that is equal to the negative change in potential energy. Or in other words, the change in potential energy equals negative EQD. So to sum this up, as this charge, this plus Q charge, moves from one side of this field to the other, from the positive plate toward the negative plate, it loses an amount of potential energy equal to the negative of the electric field strength times how much charge is on Q times the distance it travels, D. So, this is a lot like how a mass, what happens to the potential energy of a mass as it rolls downhill. What's happening is the potential energy is becoming kinetic energy. So the charge is speeding up as it zooms across the electric field. So what is voltage or electric potential? Well, voltage is defined as the amount of electric potential energy, PE, per unit charge. Or in other words, it's how much, or I should say, it's how many joules of potential energy exist per coulomb of charge. So as a charge, a little test charge Q, moves from one side of this parallel plate capacitor, the positive side, to the negative side, it's going to experience a change in potential energy. Therefore, it also experiences a change in voltage, where the change in voltage is equal to the change in potential energy divided by Q. And we saw on the last slide that because the electric field is uniform in the area between the positive and the negative plate, the change in potential energy is equal to negative EQD. Therefore, the change in voltage is that divided by Q, which gives you negative E times D. So what this means is not only is there a drop in electric potential energy for this positive test charge as it zooms across from the positive plate to the negative plate, there's a corresponding drop in the voltage. In other words, the voltage on this side is higher than the voltage on this side. So the general rule is if you have separations of charge, the voltage drops as you go from positive charge to negative charge. Later we'll see that in batteries something similar happens. The voltage is higher on the positive terminal and lower on the negative terminal. Now before we move on, there's something subtle but important to understand about voltage. And it's something that occurs with potential energy as well. If you remember, gravitational potential energy, say PEG, was equal to an object's weight times its height, or y position. And so when you give an object y position, that means you have to define some a frame of reference where y is equal to 0 or height is equal to 0. So potential energy, gravitational potential energy, is relative to where you say y equals 0 is. If you are in a building and you say y equals 0 is the roof, you have negative potential energy. But if you're standing on a mountain and you say y equals 0 is sea level, you have positive potential energy. And in the end, the absolute value, or in absolute terms, the value of potential energy is not important. What's important is how it changes when you go from one place to another. That's true of electrical potential energy. And since voltage is calculated from potential energy, that's true of voltage as well. So when it comes to voltage, what matters is not what the voltage is at any point in space. What matters is how the voltage changes, delta V, when you go from one place to another. One more thing. When it comes to representing voltage as a symbol, we use the symbol V. But the unit that we use for voltage is also V. So if you have some situation where there's 1 volt, you'd say V equals 1 V. On one side, the V is the symbol to represent the variable for voltage. On the other side, the V is the symbol to represent the unit of voltage. And you got to keep that straight in your head because they're both capital V. You know, it's not like when you do position, x equals 1 meter, or y equals 1 meter, or if you do something like charge, q equals 1 coulomb, where the variable and the unit are different symbols. For voltage, the variable and the unit are exactly the same symbol, so you got to be careful with that. So in the previous slides, we saw that one way you can establish a voltage, an electric potential, which is electric potential energy per unit charge, is to create a separation of charge. And you can do that with a capacitor, a parallel plate capacitor, for example. Another way you can create a voltage is via some sort of electrochemical means, and that's what batteries do. Batteries are essentially constant voltage sources where there's a constant voltage difference, delta V, between the negative terminal and the positive terminal. So in this case, the voltage at the positive terminal is always greater than the voltage at the negative terminal. Usually the convention is to just say, the voltage at the negative terminal is 0. So delta V equals the voltage supplied at the positive terminal. Now, we saw in the previous slides that when you have a uniform electric field, the change in voltage as you go from one side to another in a uniform electric field depends on how strong the field is and the distance you travel through the field. But in general, this relationship for voltage or voltage change doesn't apply when the electric field is different at different points in space. So a good example of that would be for a point charge, because we learned in the last unit that a point charge, here's a positive point charge, it has electric field lines that extend radially outward. So this is definitely not a uniform field. It gets weaker as you move further away, and the direction depends on where you are in space. So it's definitely not a uniform electric field. But it turns out if you use some calculus, you can calculate the voltage at a point in space, like here, for example, due to this point charge, and the voltage is equal to the electric constant times the size of the point charge that's creating the voltage divided by the distance, which in this case would be that distance, r, you are away from the charge. So there's a convention that's used in defining this relationship for voltage of a point charge, and the convention is that we assume the voltage at an infinite distance away is equal to 0. So if you have a positive point charge, Q is greater than 0, the voltage will be really high when R is really small, when you're really close to the charge, and fall off exponentially, or I should say not exponentially, fall off in proportion to 1 over R as you get further away. And R at infinity is 0. If you have a negative point charge, then when you're really close to the charge, there's a negative voltage. It gets more positive as you get further away. In other words, that's what this function looks like plotted as a function of R when Q is positive and when Q is negative. So the blue lines in this figure show the electric field lines surrounding a point charge, and then down here surrounding a dipole where there's a negative charge and a positive charge that are relatively close together in space. The greenish lines, which don't have any directionality and are closed circles, are called equipotential lines, and they're like the contour lines on a map. A contour line on the map shows all the points on the map that have the same elevation. An equipotential line shows all the points in space that have the same voltage. So it should make sense in this picture here that every point on this circle has the same voltage, because this is a point charge, and the voltage at a point in space due to a point charge depends on how big the charge is and also how far away you are from the point charge. So in other words, all of these points on this circle are the same distance, the same r away from the center, so they have the same voltage. All the points on this circle will have the same voltage, but the voltage gets smaller as you get further away. So equipotential lines always cross electric field lines perpendicularly, no matter where you are and no matter what the charge configuration is. Whenever equipotential lines and electric field lines cross, they cross perpendicularly to one another.